from this computer here. So this is so it's a really nice application for cell decompositions. Let me take all of this out. So this was your CP, right? So you're gonna see the graph as I add things, the graph will be created there. There's another map also that you can check. So I'm gonna show all the polygon points. All right. All the polygon points are pointed. So from your environment and from your obstacle, then I'm gonna show all the edges. Fresh drawing. So all the edges, so vertical to the environment and vertical to the obstacles. Then I'm gonna show trapezoids. So these are all the points. Should be able to see something here. I don't know why it's not showing. And then this last one, this vertices is, so do you remember when we talked about choosing the weight and which direction you're going? So we're gonna choose the midpoint of each of these edges, and then that will be the point that your path will go through. Now, I don't know why this is not showing, but it's supposed to show the roadmap created. Can you try it on yours? You should see the graph on that side. I don't know. I was just trying earlier. It was working. I don't know why it doesn't work. Because you have the ability to move. Oh, okay, they're right there. So you have the ability to move different points and see what happens in the graph. So if this was here, if this was here, it would interactively change that mapping for you. So you could see that how does that graph changes. So you will pick the path that you're supposed to go from there. So that's one. And there's another example. This is more complex. You can move around and then create different scenarios and see what happens to your map over there. So that's one link that I put in your today's stuff. And all right, with that, I'm going to talk about path planning that I planned for today. Now, once you have that graph, we need to decide what's the best path to go through. Now, to do that, you would need to sometimes go through all the options, then decide which option is the best one to choose from. There is no annotation for today, so whatever I write just to help me talk, explain things. So it will be just a slide decks for you guys. So path planning is basically finding a collision-free path from your start point to the state that you call goal or wherever you want to finish at minimum cost. So this cost is important. We talked about what cost could mean for every project is different. It could be time that takes you from one point to the other. Sometimes it's the length. Sometimes is, let's say, the number of turns you take. You know, if it has some implication on your actuators or how complicated your software is. So this cost, you need to identify what is cost. We write cost function, and then we try to minimize our cost function, all right? Now, there are two different strategies for path or graph search. So we created the graph already, right? Graph of the environment. We need to find what is the best path and then tell the robot that we already have the dynamic of it. Okay, now follow this. So we'll end up just telling the actuator what to do, but we need to solve everything else in between. There is one method is your uninformed search. You have no information about your environment, and it's a brute force. You know, you're gonna try everything and find the best path from there. So breadth first search, or BFS, or depth first search these are examples of uninformed search that you don't have information. The other method is the informed search. When we say inform, we will use some sort of evaluation function to decide about the information in the graph in our environment. So greedy searches such as Dijkstra algorithm and A star are those kind. We have the other kind of path planning algorithm, which is in the second slide deck that I'm not going to talk today. For example, RRT, the random tree algorithm. Those are also informed because you're using information, you're using some sort of evaluation for them. All right. So how many of you are familiar with path planning with any of these that I talked about? 1, 2, 3, good. All right. So if at any point I said something that you think, oh, we heard something different, let me know. All right. I don't want to create doubt, or I don't want to give you wrong information. So if you start from the most basic BFS. So this one, this breadth first traversal or search is a graph method that you're going to visit all the vertices exactly one time. We are going to gather information from all of this, and then we make a decision based on the information we get. So imagine having an empty table. You're going to have all the vertices. You're going to pass through them, add information to this table. Then you're going to make a decision based on information you got. Usually that what is the cost of this mission is going to impact what you make the decision that you make at the end of it. So in this scenarios, the order of visiting is important, right? And depends on the problem you're solving. So sometimes they can limit your search, or there will be, you have to visit this city or this vertex in this specific order. Then during this travels also, you have to track which vertices you have visited, because you're going to only visit once, so you're not gonna visit that thing twice. Sometimes you can use a loop, like start from one vertices, go visit all of those, come back and go somewhere else. We can create a Boolean array so that we don't visit a vertices twice. So if it's not visited 0, as soon as it's visited is 1, right? And you can easily change this when you're coding. Once it's 1, is already visited, so you're not visiting it. If you are familiar with this, we are going to have an empty array, and then once we visit, we drop them into that empty, so it means that we visited, and then your original basket will have less and less vertices to visit. It's easy because you basically are visiting everything, right? You just have to make sure that you're not visiting twice, and you collect all the information. It's nothing else. Now, this is an example. Let's say that you have a source node, and usually in this algorithm, when we are using BFS, independent from what is our goal, we are going to visit all and decide about and gather information about this graph. Then we will see, okay, what was the goal, where we want to go, and then we get the information from the table that we gathered. Okay, so you'll see that sometimes we are moving through, and then you might ask, why are we doing this? We could have gone directly to another point. The goal is to visit everything, gather all the information. All right, so the mission right now is not important, but we know that we have a start point. We're going to pick that as a source node, and that is our start point. So this is the setup. We are going to have number of our vertices. So we're going to create a let's say basket. I'll call basket for now, and we have all of our vertices 1, 2, 3, 4, 5, 6. This, we can call this area of this basket are visited. Right now we haven't visited any of those, so they're all 0. So their value from 0, 1 to 0. Then we can create a queue. This queue is usually when you start from vertices. You remember when we were creating our graph for our environment from previous class, we connected them using lines. So that's the only way that you can reach. So if there is a line, we can follow and reach. So if there's an edge, if there's a connection. If there is none, then you cannot reach to that next vertex. So once we are in one, we are going to usually look at what are the paths to other vertices, and we put those vertices connected to those as in our queue, because we were going to visit them next. So we're going to know where we're going. So we're going to tell our algorithm that there is an order in this search, right? So for this example, we are going to start And let's say we are starting, we said our point one is our node, right? We're starting at point one. We are visiting point one. So we visited point one, right? We haven't decided anything about the neighbor. So one, our vertices one is in the queue. We haven't done anything about it. Then we are going to say, okay, we visited one, cool. We are done with one. We're going to say that you print or remove it from the queue. So you're displaying it somewhere. It could be saved in another array, right? We're going to call it for now print. So we're printing that we visited one, we got information about that. Now we are moving. We can move to vertices 2 or 3, correct? Because they are the only one connected to one. So we can put 2 and 3 in the queue, and these two could be visited next. We don't have any priority right now. So in our visited array or basket, we can put 2 and 3 both as one because we don't know which one you're going to see first. And this is going to be our queue. Now, if we decide which way you're going, then we can add to our visited point from that. All right. Then here, you see what I have. Okay. So here I went from 1 to 2 and 3. So they are in my visited. So they're in queue. And I'm going to 2, for example. So 2 goes to printed, right? Then if I am in 2 more vertices are potentially could be visited. So I'm gonna give their Boolean value 1 in my visited array here, 4 and 5. Then what's the next on queue? Point 3, right? If I go to 3, the vertices that can be visited are what? 5, right? Only 5. 5 is already in the queue part, so I'm not going to add anything to it. Now, what is after 3 in the queue? 4, right? Because we are going through them in order. So if I potentially go to vertices 4, which vertices will be visited? 5 and 6. 5 already has the assumption that could have been visited before. So 6 is the last one. 6 is gonna get a number 1, will be visited, and then you can add it to the queue. So 3 goes to print, 4 goes to print, 5 and 6. Right? So you will write the code of doing that. So that's so what you've seen here. This is basically the code of doing that. Just usually writing a loop, making sure, because where do we get the information about those lines between the vertices? Like the connection, the edges, where do we get those information? Because we have to go through that. Because our computer, our robot doesn't see this really beautiful graph. What does it see? We will introduce this relationship using array, can define zeros and one, the connection between them. So if you see that here, it will go and read through these. If there is a 1 between them, to think about a matrix. If you have 2 points, you can define 0 or 1. If there is 1, means that these are connected. If there's 0, these are not connected. So basically, your code will read that line by line. And then if the value is 1, it's connected, so it will be visited or does that make sense? So to us, the graph means it is meaningful. So from our environment, we created graph, and now to human eyes, we see the relationship and we can easily follow this. But for the computer, it doesn't see this graph. So we need to introduce the information in vectors and array form for the code to understand and for the computer understand it. So here, if we visited number 6, and then we remove them one by one from the queue to the printed, and it will be done. Now, in path planning algorithm, what decides about which one is the best, most of the time is time. Which one takes less amount of time? The time complexity for this is V plus E, the time that it takes. You have to go through everything, right? So however many vertices you have, plus all the edges, you have to go through all. That becomes the time complexity. It's brutal. You have to do everything, right? There is an answer. Is it the best one? We don't know, but it's definitely there is an answer in this. You'll find a relationship. So every time you write an algorithm for path planning, always have a timer set. So it tells you how much it takes to run the whole thing one time. You could also look when you're doing research, which method you're going to use. You can check what is the time complexity of it, and then choose from that depending on the mission or the goal of your project. So this is the pseudocode of the same thing we saw previously. You saw the code. So this is very simple. You can write this for your own project. It's not in MATLAB, but it's easy. It's in Python, but you can use it right in Python. All right. So that was our uninformed algorithm, right? There are different kinds of them, but they follow basically the same idea. You visit everything. You didn't know where you're going. Now, let's say we are going from our source from the previous one. From the source, you wanted to go to point 4. So you know all the possible way of getting to point 4. You just extract that from that information. Now, for Dijkstra algorithm, we are going to, let me see if this is supposed to work. Oh, interesting. No, I'm not going to pay you. All right. So here's, you're starting from one point. There is an obstacle in front of you. So the blue ones are the new next point that you are visiting. All right. So it identifies all the possible nodes until it reaches to the goal. So here we have a goal. Our evaluation here is we can use a function for calculating distance, for example, or we can say that we want to just go and explore everything. Starting from the point you're starting, we are looking around everything around it. As you move, all the points around, and you also define the obstacles. If you do not pass the obstacle, so there is no information, there is no way for the algorithm to know which way is the most optimized way to reach. It still needs to find a way, but you see that once it reached the goal, it's not exploring the back half. If you're doing BFS, you would explore everything, right? So now if that green dot was here, all of this radius will be searched. As soon as you reach, you will stop. So if the goal changes its position, you have to run this again. While in the first method, you'll figure out the whole environment one time. So a lot of upfront work, extra time spending, but then once you've done it once, doesn't matter where the goal is, you always have the solution. So this is usually better because you usually have an obstacle in the course, but you usually have a goal. And once you reach the goal is to find the goal, right? You don't want to figure out the environment. You have to find it. So this is one example. How do I go back? Okay, let me figure this out. Stop sharing, back. Stop testing. All right. So we started from the lowest cost from the very beginning, and then they exclude all the neighbor vertices as we move forward. And once you reach the goal, you stop. So a simple example, again, now you can follow this example, see how those points were populated. All right, how many of you have done this before? It'll be useful. All right, great. So again, let's say we have a graph. This time we have these edges are weights. So how do we find those weights? Adam, where do we get those weights? So do you remember in the example I showed you with the real nice app? They find the middle of the vertices, and then you can vertices and you can measure in between them. So that could be how this is rated. So depending on what the project is, the cost of going from one node to the other is the weight of that. All right. Now, depending on what the project is, the weight is different. Now, in our application, it's usually distance, right? The distance from going from one place to another, it will identify as the weight to that. So from node A to B, distance is 10. From A to C, distance is 3. So basically, you want to find not always the shortest path, but usually the shortest path between 2 points. All right. Now, we're following kind of similar approach as before, but now our decisions are more informed. There is more information attached to our decision. We don't just go and get everything. So our Q is the vector that we put all of our nodes, and you're going to say wherever your start point is, you're going to give it a 0. So that is your visited, or there is no way to it, 0. Everything else is infinity. Why do you choose so much of a big number? We don't have any information yet, right? So any other number you give, then there is something greater than that. So we just call it infinity. So meaning that all the distances right now are the same to this, right? And then we're gonna have our visited node or vertices vector as well. So once we visit something, we can populate this. This has to be emptied or numbered, something other than emptied. This has to be filled out with all the available vertices until the end or out. Right? So if you're defining a for loop, that's you're having an index, making sure that you move to all the way to the end of your indexes. All right, so starting from point 1, we are gonna go and say that, all right, what happened? How did I get out? Oh, I just did this. I am still in Zoom. Back. Yeah, I don't know. All right, back again. All right, so I am in point A. That's my starting point. There are 2 paths, so it's kind of similar things. You can go to point B or you can go to point C. The cost of going point B is 10. The cost of going to point C is 3. Now we are gonna put those numbers in our visited queues. So I populated that to get to point B, it costs you 10. To get to point C, it costs you 3. Now here's the thing: as you move, these weights accumulate. So you pick up the weights with you as you move forward. That tells you like how much it will take you to get to specific vertices. So right now I'm done with A. I could be at 10 or I could be at 3. So in this algorithm, what you want to do is you usually choose the least weighted path. So that's where it differs from the previous one. Previous one, you would go to both of them, right? So if the problem is the shortest path, which usually is, I'm going to go from A to C. So now this is becoming my reference node, and I want to know what are the ways to go from this C to the rest. Okay, so, and I already visited A, I already visited C, so I'm populating those. Now, from point C, if I want to go, so let's find out how many paths or edges exist to the other node. it doesn't matter if you already visited one. We can again explore the our option. So from C to B, it would take me 4 unit cost. So I'm gonna add that 4 unit cost. I'm gonna consider from C to B 4. So 3 plus 4 is going to be 7. So the new number for B was going to be 7. From C to E is going to be 2 points. It costed me 3 points to get to C plus 2 points to E is going to be 5. And to go to point D is 3 plus 8 is 11. So you see that your previous steps is impacting where you're going to reach next, right? So between those, which one would be the next step that you would go? Again, you will look at the lowest cost, right? So I'm going to look at the lowest cost. I'm going to be here at E, and I'm going to say that, no, your lowest cost would be, yes, E, sorry. I'm going to be at E, lowest cost. E is connected to D. That's the last point I haven't visited yet. So I'm going to find out how much it costs from going into my point D. Now, everything has been visited, and I find out I'm missing something here. B. Okay. So I visited E, correct. Then I still have to go and visit. So this is E to D is 5 plus 9 is what? 14, right? Previous number was 11. So I'm not going to increase that. So I know this is the wrong path to get there. So I have to go back from the previous path. So we have to go back and go from our point here. I did not visit B yet. So I visited E, I have not visited B. To go to B, I can go to A, from A to C, C to B, which will cost me 7. So I'm gonna keep that 7 as the same number. So it's cheaper to go from the previous point, correct? So I visited all of them, but I kept the path of the least cost. If a new path had more weight, I'm not going to choose that. So as you're moving through this, you're already choosing the lowest cost. This is an informed search. So you have the knowledge of your previous steps. So we visited the last point that was B. And from B, we are here. From B to go to D is going to cost me 2, right? So whatever it costs you to get to B plus 2 becomes the new value for D, which is 9, which is less than 11 from previous slide. So if you wanted to go to D, it is better to go to B, not the previous path that you took. All right. So when you found the least weighted result in this exploration, in this search, so you are done, and this is, if you wanted to go to E, you will go, you know that it will cost you only 5. Then you pick a path that it will take you 5 to get to that point. All right. Now, this is the pseudocode, if you wanted to follow and if you wanted to write the algorithm. Oh, I don't have that one. Hold on. I have it on. So now, would something like Dijkstra be the best way of doing? Why not? And what are better ways to do this search?
You're often going to have to search very large space anyway, so it's going to end up being very close to first search, because although you're like taking into account like what's shortest, you don't really have any information about where you can get once you're somewhere. You have to like keep searching.
So what could we do? What can we add to this search that we can get a more informed way of deciding about our next step? So remember, we had this obstacle, we started from here and we explored everything, right? So if we have our goal, we know where our goal is. If we could measure distances, for example, from here to the next point also, which next vertices, if we could have an evaluation function, what's the shortest path to get to the next one? That is closer to our goal. And if we follow that, then we will reduce the amount of calculation. So Dijkstra already uses some vague information from the environment, right? Between all vertices. Now, if we could add a function that actually calculates distance, the actual distance between where you are and where your goal is, you can only take the nodes that are closer in distance to that node. So you don't have to explore everything, because you're right. When the environment is large, BFS might actually be better because you're exploring everything. Your Dijkstra will be like your BFS. As you saw, there was that if your goal point is really close to the end of your environment, you're basically exploring everything. So, why is this not playing? I'm gonna just show my, of this one here. Yeah, I'm gonna show that on Zoom, so hopefully it will work. We'll see. Hey. All right, so this is your A star. It knows the goal is on the other side, right? So it's calculating the distance, and everything in the straight path is going to be shorter, but it knows there is obstacle. So it keeps going around the obstacle until it finds the shortest distance. So physically find the actual distance between where you are and where your goal is. Now, if you move that goal, if this goal was here, it would only go and explore because it will find what is the shorter distance, right? So whenever you add a second function that calculates, let's say, distance here for you, in addition to all the weights information you had from the environment, that is a more informed search. So you're doing the least amount of calculation. Let's see if I can go to the next slide from here. Now, see the difference between the two and see how much faster the other one is. Can you see those little gray lines between nodes? Right? So it has the information that I can be connected to this. If you think about this, is just a mosaic, right? It connects everything together. Now, well, the other one already arrived, right? And then repeating the algorithm again. So it is on cycle, so you see that it keeps doing that. But if you see the amount of calculation done on this side is a lot less, this will be faster, just simply because the processing time of exploring the nodes. Yeah. So now sometimes I think that was the end of that one. So sometimes, depending on what is the mission, what are you exploring? Sometimes BFS search is good. You get all the information about your environment, it's a simple environment. You want to keep repeating the same path that you're going. Maybe that's a better solution for you. If it's complex, it's an like real-time online calculation, like the path planning. You don't want to spend all your processing power in exploring the whole environment. That's not easy. Okay. Now, I'm going to show you the RRT videos because you have time. So those of you that use these in your project, can you talk about, for example, can you talk about what project you use this and then like what algorithm you use? Yeah.
So I use it's a modified version of A-star that lets you find the project I'm working on is drones flying wildfires. And I want to find the minimum time resource expenditure path that can also keep exposure to deflecting fire below us. So it's a resource constraint path, not a problem.
Interesting. Do you know like what is the kind of time like timestamp that you need to process and get the information? Like how fast the algorithm should be?
It's a global planning algorithm, so like maybe a second.
Okay, and then so you're using a star let's see, like modified A star, right?
Yeah, it's called hybrid A star, so it's
Mhm.
X, Y, and
Who else? Someone here raise their hand that they're using path planning. Any of you? Where do you use path
I
planning?
am, but it's another software.
What do you do?
Doing novel to the path planning for basically if you have basically a spray coating that you want to have on a part, being able to determine the path plan for an end effector that would yield the optimal paint, like finish on that part without having any human interaction.
So it has to basically paint everything. It has to visit every single point of the environment.
Yes.
In the environment that's this workspace, right? So you're finding the most optimal way to do that.
Yes.
So optimal is time or what?
Well, you can't even get to optimal because the state space is too large.
Okay.
So it's just finding a way.
A way, okay. What, okay. So what did you say, which method do you use?
Oh, none of these.
Okay.
We had to come up with new methods.
Okay. So the other method is rapidly exploring random tree or RRT. So you usually have some place to start and some place to end as your goal, and you have obstacles. So in RRT, you're gonna kind of like branch out, and you're gonna say you're gonna define interim goals. Let's call it that way. You're gonna say, I know my goal is over there, but I'm gonna pick a goal very close to me. I'm gonna reach to that one. Then I'm gonna pick another goal. I'm gonna reach to that one. So while you're doing that, you're exploring your environment as well until you reach to that final point. And you're gonna say, from all of these, I'm gonna choose the shortest one I got it. Because you're kind of like exploring around where you're going. So it's like parallel computation. At the same time, you're exploring different paths, and then you can connect them. So it basically works based on the nearest position from where you are, from your start point, and until you reach to the final point. Here is, again, another pseudocode if you're interested in RRT. So a simple example is that you're going from here. So you should be able, if you run this links, you should be able to see the video. I think I have a video in this slide. So one way of doing RRT is bi-directional. So instead of just exploring from your goal and setting midterm or a nearest goal to your starting point, you can do the same thing with your goal. So explore from both ends. Then once these branches connected, you stop and then find the best path. All right. RRT or RRT started. RRT start can find your optimal solution. They are usually very favorable in so this is a robot that doing pick and place and is using RRT and RRT start. So it's basically finding the path to go to these 4 points and then pick basically what option is the most optimal to do this. First, moving all these 4 objects and which one is the faster here for us because of the least distance. And so basically put all 4 of them. Because both of these, there is a path, right? It's just trying to find which is the best one for them. So again, watch the YouTube video of that one. This is a robot with an obstacle. Here's RRT. You see all the different paths that this robot can take to get there. Watch this video. Here, I wanted to show you the probability roadmap. This is very random. So maybe that's what you should do, Adam. Use RPM. So randomly finds points next to where it should go, explores from them, it connects, and then finds a way. This is very interesting. Watch this. It is in MATLAB. You should be right now very like well versed in MATLAB, at least in our field. Ow. So for the RPM, let me see if I skipped one. Okay, yeah. So the RPM procedure, you're gonna say that, hey, I define my free space. I'm gonna choose a random sample, different samples, randomly. I'm gonna pick 50 points, right? And then you're going to try to start from one and connect those random points, like connect all the neighbors together. Once everything is connected, then you find the best way. Since the points are random, right? So there is rule found. Then after you connect it, you do the path smoothing, and depending on your vehicle, you find the best way. Yeah, so Dexter, well, breadth force, Dexter, A star, RRT, RRT star, RPM. They're very famous basic path planning algorithm that you could use, especially with autonomous vehicle or industrial robots. Yeah, so we usually get to explore more on path planning, but this year didn't have time. So, but all the information is in these slides. If you want to explore more, you can always email me and I can give you the couple of homeworks that I had. So you can not to do it in one time, because those are MATLAB codes that it gives you a map of the environment. If you remember for the continuous with the one with LiDAR, that you have point cloud. So you can get the point cloud information and how are you going to choose the path. So MATLAB has a really nice example. If you are interested, you can send me an email, I'll send you that. That used to be a homework. I'm not doing the homework. But they would just spend time doing that. So that's about it. Let me pause the video so don't write everything there.